Okay, so hold on. I just need to make my final settings, and then I need to tell you how was my day so far. So we're in here. Yeah, it's supposed to be okay now. It's 4:18. That's when I'm gonna again do my video editing. This is a point that we will get started for today's lecture. Um, so let me tell you what happened just a few minutes back. I've been a little bit annoyed because of the fact that whenever I'm sharing my desktop, is always a big mess. You know, is that there's a lot of stuff in my desktop and it looks nasty a little bit. So I thought that I'm gonna make a little bit of surprise to you. So I will clean my desktop and I will install a camera. So you see that I'm no longer using my laptop camera, but I'm using another camera that is located in the top of my screen. Now, when I was cleaning the desktop, something really, really weird happened. And what happened was that I actually lost the presentation for today's lecture. And I was spending last 5 minutes or so to building another one for you. Um, and and it's for that reason that the lecture material today is not really perfect. It will be okay, but it still need to some modification, and maybe I need to adjust that when I'm delivering my lecture today. Okay, so we'll see. What are the other comments? So there are comments that it may be a good idea to place the lecture material to Moodle prior to lecture. Sure, that's a good idea. It's just that it needs a little bit of work from my end because I need to make two different versions. One that I'm delivering here during the streaming, another one that I could place to Moodle database. And the reason being that if I would use the same version, then you guys will see what are the in-class quizzes. And that's a good percentage of the fun part. And I don't want to lose that fun part. But let me think about that proposal. Let me think if I can help you in that regard. Uh, what are the other comments? Okay, so yeah, so it's a little bit about the streaming quality. But still, before we jumping into today's real deal, real matter, let me tell you something. I'm about to purchase a green screen that will be in my background. So I'm planning to invest a little bit about the streaming quality. So my plan is to take this YouTube career seriously, and I wanted to make it such that my from this up will be visible in my PowerPoint presentation, and the background will be disappearing completely. We'll see if I'm eventually able to do that, but that's a little bit of my dream. Anyway, so we are not here to discuss about the streaming quality and not here to discuss too much about other practical matters, but how is a simulation of a mechatronics machine. Now, as promised, today we're going to move on to hydraulics. The first three matters that I'm hoping you to explain you today is the properties of fluids. That's some the properties of liquids and fluids. That's going to be something that I don't think that I need that much time to explain it because even though that there's a lot of different properties in fluids and liquids, we're only going to look at two of them because others are less significant what comes in the modeling. And the important properties we're going to look is a viscosity, which is not very important. And it's not very important because it's only needed instead of the laminar flows. What is a laminar flow? That I will explain you, I guess, next Monday. But it's not that frequent property that is needed. Another one that I'm about to explain to you is a bulk modulus. Bulk modulus for sure is extremely important. It is needed in a lump fluid theory. Lump fluid theory will be the next item that I'm about to explain to you. If there is one subject matter from the modeling that you need to know, that is definitely line fluid theory. And now I need to still do a little bit of changes in my window to see what are the comments. Okay, so line fluid theory, that's what I'm expecting you to learn today. And if we have a time, like I think we have a time, then we're going to look a little bit about the flow types. And now, again, because of the problems that I'm facing with my presentation today, maybe we even going to have a break after a little while of explaining things related to properties of fluids and line fluid theory. We'll see how we are progressing today. But remember, the last Monday was not the great lecture. There was if I remember, a little bit of problems in my explanation. There were a little bit of problems in technical matters. So I was hoping to impress you today, like, using this camera and so on and so forth. But I lost my presentation, so it's not going to be impressive lecture. So hopefully next Monday will be something that you'll remember the rest of your life as an outstanding lecture. Anyway, so let's move on. And I see that we're collecting more viewers. Now we have 59 viewers, which is already okay. Now, last week, I think that it was on Thursday, I emailed you a message via model database that we want to change the grading table from the first midterm exam. And the reason being that this question that I started to explain on last Monday, it's solvable. It is solvable, but it's not that clear. And why it is not that clear? The good explanation was, of course, in my previous PowerPoint presentation, which I lost. So I don't have a really thorough explanation to you. But let me try to explain to you why this is a little bit of a challenging task. This is a question where we're expecting you to solve the third component of the generalized forces. Generalized coordinates. Maybe the easiest way to solve this is by first looking at what are the generalized coordinates. Well, for the one body like this, pendulum kind of body, we have three generalized coordinates. The one that is Rx, Ry, and angle theta. Now, the generalized forces will be associated to these three coordinates. And we're expecting you to give us what is the last component, what is a numerical value for the last component. That you can solve by simply substituting all the information to this equation. And in this equation, we have here force, which is provided here. Numerical values are provided here. Then there's a rotation matrix that is differentiated with respect to angle theta. When I look at my streaming window, I can see that I got no viewers anymore. Let me see. I need to check that I have a recording on. Yeah, I have a recording on, so at least I can save this through the recording. So if you guys are unable to see this, oh, you there? Okay, it's just that I got an information that I got the 0 viewers. I don't know why, because I'm monitoring comments and I'm monitoring the number of views and this kind of statistics. So I was about to explain this guy. So this is a rotation matrix differentiated with respect to angle theta. It is the one that is shown here. So let me take a magnification. So this component here. And then finally, the vector u bar is this guy here. Vector u bar. Okay. Now, vector u bar is the one that is a problem here. And it's a little bit of a problem because, it's clear that the body reference coordinate system is located here in the center of the beam-like body. But axis orientation was not provided. Now, if you select your axis orientation in a way that we usually did during the exercises, such that this transverse direction was denoted as a y, and axial direction was denoted as x. Then you got the numerical value that was not provided as one of the correct options. So that was not obviously the way to solve this problem. So then the way to solve it was to switch these axes, to put the y here and x here, And then when you compute it, you get this as a correct value. But now, because it was about the selection of this body reference coordinate axis, and that information was not provided in the exam, we decided that, of course, because we want to be your friends, we all want to be friends, we want to love each other, and so on and so forth, we want to modify the grading table. And we did not modify the grading table such that you will get more benefits than just a few points. But the few points, I think it still make a big difference. I think so. And now the new grading table is the one that I emailed to you. Now keep this in your mind. We did not change the grading in a model database. So this new grading table will be accounted when we are comparing the final grades. So that's when we're going to take that into account. Prior to that, you just need to keep it in your mind that you will get some compensation, and it will come a bit later. Right. So with that, we're still gonna get like weird comments, not comments, but weird statistics in my screen. Every now and then the view numbers go zero. So still the information that I have is that the connection is excellent. So I'm expecting that all is going okay. Yeah, the new table there regarding the second midterm exam, the original table will be used, not the modified one, but the original one. So again, you don't really see much, but you will see that modified grading when we are computing the final numbers for this course. Now there was a question about weekly assignment number 7. So weekly assignment, or the correct values or the correct answer for the weekly assignment number 7 will be available a little later today, because the deadline submitting that assignment was last night. So I'm going to release the correct information right after this lecture. You just need to, hopefully that stays in my head, because my memory is strong, but it's short. It's so short that even if I say that I promise to do something, maybe I'm not going to eventually do that. It's not that I'm do that intentionally, but it's just that it goes off on my head. Okay, so hydraulics. Let's discuss about hydraulics next. One of the important things about the hydraulics is that when we are discussing the hydraulics, we're going to focus on the hydraulic circuits. Hydraulic circuits such that we will get started from the motor, which could be eventually, the real life, it could be a diesel engine, it could be electrical motor like it is on here. So this is a motor that is running the pump. Then the pump is the one that is capable to produce energy to hydraulic circuit. Now, how we're going to describe the hydraulic circuits will be based on these hydraulic symbols. So we're not going to show the motor like it is shown here in a 3D figure. We're not going to show the pump like it is shown here, but instead it will be those drawing symbols. And now, if you are not familiar with those drawing symbols, it is highly recommended you to go and take a look at this material from, I don't know, engineering handbooks or other YouTube channels. There's only few drawing symbols that we need to deal with. We need to deal with the pump, then different kind of direction valves. So take a look at what the valves is and what these different ports and different connection opportunities or possibilities, what they are standing for. Then simple kind of throttle valves, those is good to know. And then actuators, and this is a hydraulic actuator. Those are what I'm expecting you to know at minimum. And again, this kind of representation of hydraulic circuit will not be used from this on anymore. But we can have look at how is a hydraulic circuit by using these drawing symbols. But it's just for your information, real life, this guy here is a hydraulic cylinder, and it looks like, well, hydraulic cylinder. I'm sure you have seen millions of different hydraulic cylinders. This guy here is a direction valve. physically look like a chunk of steel. Inside, there's all different possibilities and the ways that you can use to control the hydraulics. Okay, and just one more thing about the last week lecture. Why this hydraulics? By the way, I had a first in-class quiz for today, which was why it makes sense to model the hydraulics. But I lost it because I made a mistake with my files, so I need to explain it to you. So why it is important to model the hydraulics? It is important to model the hydraulics because otherwise you do not know what are the actuating forces. And if you don't know the actuating forces, it's actually not making much of a sense to build a very detailed and accurate multi-body model of mechanical components. Usually, actually, in engineering perspectives, it makes sense to follow the principle that is like equal accuracy approach, which means that different disciplines, say mechanics and actuators, are modeled roughly with the same level of accuracy. Because if there is a very detailed model of mechanics, and then you're just guessing how much force is produced by hydraulic cylinder, the one that is here, you just say, okay, I don't know, maybe it's 15,000 newtons, and then it's fluctuating in a certain way. Then it actually is not making any sense to build very, very detailed and sophisticated multi-body model. So what we try to do from this on is that we're going to look at the ways that the actuators can be described. The reason why we do that is that we want to know the forces. The forces that are then applied to mechanism. And once there is a force applied to mechanism, that is the way that we can introduce the machine that is capable to move, capable to do some real operation. So, okay, finally. So let's get started. First thing that I would like to explain to you is properties of fluids. And like I mentioned, there is modeling-wise two important properties. And out of the two important properties, one is really important. Second one, good to know, but all in the special cases is important. Okay. Now, viscosity and the bulk modulus, those are the things that I am going to explain here next. And we will get started from the bulk modulus. First in-class quiz, by the way, will be related to bulk modulus. And I'm asking, well, I can already tell you this, and I think that I need to put my Socrative on, by the way. I'm asking, what is a physical interpretation of bulk modulus? It is a flexibility due to the hydraulics. Now, let me just first lock myself to Socrative, and then you can see the questions here. Which is this one? Oh, no, not the right. I need the launch here. That's what I would like to launch. Okay, so it says, oh yeah, one more thing. I think that I need to finish this because, again, I was teaching in St. Petersburg, and because I was teaching in St. Petersburg, my class is, my room is not the correct one. So let me see, what is the room that I want to use? I want to use room LUT. Now I'm in LUT room. And the squeeze will be on momentarily. Yep, I see you guys here. I'm not gonna ask you like why it is important to model the hydraulics because that is missing from my slides. But my first question is that bulk modulus in hydraulics describe, and then you see the different options. Okay, viscosity. This is something that is important when we are looking at the laminar flows. Now, even though this time I'm going to mention you that we have two different types of flows. We have a turbulent flow and laminar flow. Laminar flow takes a place when the pressure difference is small. Well, that's a little bit unclear statement. Small as a rule of thumb, means that when the pressure difference over the throttle is say less than 5 bars. So we could have a situation like this. So we have here a pipe, and inside of the pipe there is a throttle that is restricting the flow rate. And the pressure difference means that how much is the pressure this side and how much is the pressure this side. And the delta P is the one that is described as a pressure difference. And now, when the pressure difference, this guy is small, and I'm saying small, that would be less than 5 bars, then it's possible that the flow rate is having the laminar type. Laminar type means that, the particles, by the way, they're traveling with the, good order, so there's no whirling, but they are moving smoothly. And that is not very common, particularly in application where we are, or what are the applications that we are discussing about. Let me take a look at what are the comments here. Yeah, you see the second comment already, because the first comment I was have to skip because of the problem in my presentation today. So unfortunately, we move right to second in class quiz. Yep. Okay. So thanks. So there was an explanation there. Right. So laminar flow takes place when the pressure difference is small. Usually, when we are speaking about hydraulics and mechatronic machines, applications in our mind is mobile machines. That's a good example. In mobile machines, it is very usual that the pressure difference, this guy here, is large. Say it could be 100 bars, it could be much more than that. And if that's the case, then the flow type is a turbulent flow. It is very, very common, much common than the laminar flow. Anyway, so viscosity is related to laminar flows, but the important matter where we're gonna get started is a bulk modulus. And as mentioned here, it is a description of flexibility. And it's a similar kind of quantity than elastic modulus used in a strength of mechanical structure. So it's kind of defines how stiff is a system. And it is something that is extremely important because there are cases that overall flexibility of machine is mainly coming due to the hydraulics. And only the very minor contribution comes from the deformation of mechanical components. And that's something that is, the flexibility of hydraulics is so significant that we have to take that into account when we are computing the pressures in different locations of hydraulic circuit. Okay, so how is this bulk modulus then? How is that we can compute it? Okay, that's actually is very simple. And to understand that, we have to set up an experiment here. An experiment is such that we're gonna build a unit side container. Unit side container will be made from the material that is rigid. Well, you know that in real life there is no such thing like rigid material. Every material is a deformable material. But let's just hypothetically say that this is a rigid container which do not deform no matter what. And then we have here unit amount of fluid inside here, and then there's a lid, and the lid too is made out of rigid materials. Although all the mechanical components here are rigid. And then what we're gonna do is that we're gonna pressure the lid inside of this container, and we are using quite a bit of power, something that is needed to compress the fluid. Like, look at this. This would be enough to do it. So enough to, the pressure to this lid down. And when do that, the volume that is in the, associated the fluid here, that's going to be decreasing. How much is going to be decreasing? It's going to be decreasing amount that is called dV. So it's a small amount that it is decreasing. So it's compressing. What happens simultaneously? It's that the pressure will increase. So the pressure here inside started to increase while the volume gets smaller. This bulk modulus is all about how is this ratio between the pressure change and volume change. Again, pressure increases, volume decreases. This ratio is called bulk modulus. Now remember I explained that this is a unit site container, which for us is not very handy because we could actually wanted to make this applicable to all different kind of applications. So what happens if we wanted to extend this to all size of containers? Maybe that would be the better way to say. Let's all size of the containers. It means that we have to take the volume size into account. So let's divide the whole thing about the volume size, and then we're going to have here minus original volume size, pressure change, volume change, and that's going to be called as a bulk modulus. And now I need to take a look at the comments. Okay, so my face is too big. Okay, so let me modify. Yeah, it is too big. I see that. Sorry about that. Let me see, where's my OBS? Here is my OBS. Yeah, I was so impressed about the camera and everything, so I thought I was accidentally make my face too big. Now it's okay. And I was here. So I was about to explain how is this bulk modulus. And I can see that you guys are putting the game on already, which is related to success rate of the first in-class quiz. Okay, this is what I explained already. So the bulk modulus is pretty much same than elastic modulus used in mechanics. Now, in real life, bulk modulus is somewhat complicated matter, and it depends on number of functions. So it is a function of a number of different items. It is actually a function of the pressure that is applying. It is function of the temperature, quality of fluid, and so at least those three things affects. Now, in modeling, in hydraulic modeling, we have to cut the corners a little bit. Not little bit, but quite a bit. Meaning that there is no way to take all these things into account. And that means that the way we're going to introduce the bulk modulus is that we can simply assume that to be a constant, or is that, and we assume that to have a constant value. And you see that that's not exactly according to reality. This is the first assumption we are doing in the terms of modeling of hydraulics. There will be number of similar kind of assumptions that are coming soon. Now, this bulk modulus, or the modeling of the hydraulics, we are usually setting the bulk modulus to be constant, and the usual number that is used is a 1,500 megapascal. Now let's look at the picture, which is a very low quality picture, but it's located here. So this is telling how the temperature, which is the x-axis here, and the pressure actually is the curves here. This is effective. This is a bulk modulus, how the different pressures and how the different temperature is affecting or are affecting the bulk modulus. And you see that, yeah, they're actually having some quite serious effect. Even though that they have some serious effect, we're still making an assumption that bulk modulus will have a constant value, and the constant value will be set to be somewhere here. So 1,500 megapascal. Okay, so let's move on. Now, I mentioned in the very beginning that the experiment was such that, so screen is a little bit off again. I guess that is okay now. So I mentioned in the very beginning that in this experiment, I built this container to be rigid, and this lid was rigid as well. And I was making an assumption that there is no dissolved air in this fluid. Those are the things that are, in real life, very hard to do. Because first of all, as mentioned, the rigid body is non-existent thing. Every single body has a mechanical deformation. And if they have a mechanical deformation, this will affect the flexibility. You know that. You understand that if this container is made out of the rubber material, and then you can introduce a big force to this lid. Again, this is a big force that is coming to lid. Of course, container will expand. The fluid will compress, but the container itself will expand. So there is a mechanical deformation, which could be, in many cases, very significant. And then, of course, just having the fluid without dissolved air, that's a little bit hard to do. Then what we need to do is that we need to extend this concept of bulk modulus such the way that all these real life components that are flexibility of containers and dissolved air must be accounted. And the way they can be accounted is that we can compute something that is effective bulk modulus. So here it is again. So definition is a bulk modulus. Bulk modulus tells you how is a flexibility of fluid. But because there are other components in hydraulics that affects the flexibility, that's why we're gonna extend this bulk modulus and we're gonna look at the effective bulk modulus, which effectively contributes to the deformation. And now how that happened then? How that happened? By the way, I like this comment which is related to these generalized components. So there are 3 generalized components. So I kind of realized myself that I was repeating quite many times that when we discuss about multi-body dynamics, that each body has 3 generalized coordinates. I'm gonna make a song out of that, and I'm gonna sing that song to you when you're gonna have a last lecture. But before that, let's look what is that we can do when we have a real system, the real case here, the real case where we have 2 containers that are connected together in a way that the connection is not introducing any pressure losses. So later today, you learn that this kind of system where there is no, hold on, I need to put it this one here. So this kind of system where there is no pressure losses between the container 1 and container 2 can be considered or can be accounted by using one differential equation. So there is no flow restrictions between the container 1 and container 2. Okay, so let's look at this situation. Now the total volume obviously can be computed such the way that is a total volume of fluid in container 1, total volume of fluid container 2, which is exactly the same than container sizes. All right. Now what we're going to do is that we're going to introduce a mathematical difference right here. So we're going to we're going to change this total volume here. We're kind of introducing again some kind of lid that is compressing the system. So what happens in this case? Well, the fluid will compress again, but the containers will expand. So that's why the plus and minuses. So fluid will compress, containers will expand. Okay, so what next then? Hold on, so I'm here. So I am here. Okay, what next? Next, we can use the definition of bulk modulus, which is this one here. Using the definition of bulk modulus, we can derive these relations, which is a change of the volume, what are the change of the containers, and this will be submitted to this equation here. All right. And what we're going to get as a result is this one here. And then we're going to take these guys, volume, total volume, size, and the pressure difference. With the pressure difference, by the way, we can get rid of because it's a both side of the equation. And when we're going to take this total volume in another side of the equation, we get an equation like this. Here is something that we are really after. So we are after this effective bulk modulus. This is an equation. I think I compressed a key some kind, but it seems to be okay. So here is the way you can compute the components that is affecting totally to flexibility. Now, let's take a look at that in a second, but let's move on here. Now we're going to make some simplifications. So we're denoting that the total volume is a fluid number 1, fluid number 2, and the container size is roughly the same than the fluid container size. And when using this simplification, the effective bulk modulus can be written like this. Let's stop here and let's look what we have here. So we have here, first of all, flexibility of fluid is this guy here, the one that we assume to be 1,500 megapascal. Then we have here how much is size of the volume number 1, container 1 number 1, total size of the system, and the flexibility associated to container 1. How to compute that? I'm going to explain that to you in a second. And the same for second container. Now these are the contribution that is coming from the flexibility of containers. Similar procedure. We can extend this and take another volume into account. Another volume that is very often used is the volume of air, because whenever you deal with the hydraulics, it is common that there is a certain amount of dissolved air in the system. Air that comes when you do the assembly, when there is some other problems in the system. There is always a little bit of dissolved air, which can be accounted by simply assuming that there is a certain amount of volume of air, and that is respect the whole total volume of the system, and this is a flexibility of air. Flexibility of air is roughly 1,000 times smaller than flexibility of fluid. You know that. You know that easily because, you can take a pump, bicycle pump, and you can close another end of the bicycle pump and you can move piston. So it's going to be easy task to do. You can easily make it happen. But if you put the bicycle pump to be full of water, oil, if you want, and then you close the end of the pump, then the piston is practically very, very hard to move. So it's almost impossible to move it. Now, this is an example that, the air is really, really much flexible than the fluid. By the way, sometimes people are saying that, the fluid is not flexible. So it's not really the case. So it's rigid. It's not rigid. And let me tell you why. If we would be in a lecture room, which is fully occupied by air, when I'm explaining something to you, you hear me because, what happens is that when I'm speaking, there are these waves that are traveling in air, they're traveling from my mouth to your hearing system. And in your hearing system, you recognize that I'm saying something, and that's the way I'm teaching you. Now, if we would put the lecture room full of the water, you would probably still hear me, but you would hear me like this, like maybe this is how you hear me right now. But I'm sure you all been in a swimming pool, and when you go under the water, you wanted to speak something to your friend. It's possible. You hear the talking, but it's really, really difficult to make it understandable. Okay, so that's a proof that the water is flexible too, because here, it's flexible because the waves are traveling in air. That's the way you can understand me. That's the way you can hear me. In water, if it would be rigid, there would be no way that the waves can travel in water. Okay, so with that, let's look here. Let's look a little bit about what is an effect of dissolved air. This I need to make a bit bigger. So I have here 5 different curves. These are like theoretical assumption how much dissolved air is changing the bulk modulus. And again, this is an effective bulk modulus. Here it is assumed that the bulk modulus is a 1,800 megapascal. We made an assumption that it is 1,500. Okay, you see that if there is a 0% of air, then there's no effect whatsoever. If there is a 15%, which is quite a bit, maybe it's a little bit extreme case, then you see that the bulk modulus is lowered significantly. really significant. And if I look at the x-axis here, these are the pressures in megapascal. So this would be 100 bar here. So even in 100 bar, it is lowered percentage-wise quite significantly. So dissolved air is a significant source of flexibility. Another significant source of flexibility are the hose connections. Typically, if I need to, hold on, this is like this. If I move back to my hydraulic circuit, this one here, these pipelines or lines that are connecting different components together, they may be made out of the steel pipes or rubber/steel hoses. Rubber/steel hoses will be quite more flexible than steel pipes. And that's simply because of the rubber material. Even though that there is a steel net inside of the hoses, their flexibility is still much more significant comparing the steel pipes. But because of the many practical applications, you need a little bit of flexibility. Maybe this cylinder is in an arm that is moving, and you cannot build these connections by using steel pipes. You have to use hoses. So if you're using the hoses, it's expected that that will affect the flexibility of hydraulics quite significantly. How significantly? Let's look at the one experiment. So these are the results that are really old, but I found it from one of the textbook. So these are the measurements, and the measurements are made such the way that there is an internal pressure. An internal pressure is again provided in megapascal. So this one here is 120 bars. And how much they affecting the effective bulk modulus. This is a huge effect because look at the values here. In 100 bars, the curve fitting techniques is providing the values that is here roughly like I would say 340 megapascal, roughly that much. Think about the flexibility of fluid itself was this much. So it's lowered quite significantly. And why? That's because of the hoses. So hoses is the source of reduced flexibility. Okay. I see that I spent the first 45 minutes. So what do you guys say? Should we have, let's go through this explanation that you do need in order to answer this weekly homework. By the way, I think that this is the last week that I'm introducing a new weekly homework. I think it is the last one. And once I'm done with today's weekly homework, there is no more homework to go. Think about this. So we're getting close to wrap this course up. So a little more effort and then we're done. Okay, but this is what you need in order to answer this week weekly homework. Yeah, so there's a question like, is there then only project work and the lectures? Yeah, actually there is only thing that is left is project work and then the next midterm exam. And lectures, of course, if you wanted to follow these lectures. I don't know if you wanted to do it. Oh yeah, so there was a question what to do next. Well, you can go back and forth in the YouTube recordings if you're suffering from sleeping difficulties. I can guarantee you that if you're suffering from that, my YouTube channel can fix it. Maybe I could maybe this would be the way to collect more views. And yeah, the last exam. No, there is no last exam. There is just the next midterm exam and then we're done. So that's it. Okay, I'm going to explain the rules you one more time next Monday, but not today. Okay, this week weekly homework is such that I'm introducing the simple mechanical structure, which is something pretty much like this. And it is actuated, oh my God, the handwriting is really, really bad. Then I have to, I'm sorry that I interrupt you my explanation, but it's, these Tupecon comments, it's so nice. I like them so much. Okay, this kind of mechanical structure, again, there is just one arm, and this arm, one arm, there's a mass, free end of the one arm, another end is connected to ground by a revolt joint, and then there's a hydraulic cylinder. And I'm asking, what is the frequency, natural frequency of the structure? And in order to compute the natural frequency, we do need to know two components. We need to know mass. Well, that's going to be simple because you know the level, you know this length. Oh my God, you know this length, you know this length. So you can introduce how much mass is the top of this hydraulic cylinder. So you can make an equivalent system where there is a mass that the hydraulic cylinder is lifting. So this mass goes here. Another component you need is stiffness. Okay, stiffness. This is how what we can compute with help of effective bulk modulus or bulk modulus. So how it goes then? Well, stiffness. You know that the stiffness, you can get it when you know the force change divided by displacement change. Okay, that's great. That's great because these are the stuff that I can compute by using this simple hydraulic system here. All right. Again, the mass is here. The mass going to go here. Stiffness, that's what I'm about to compute. And I can get the stiffness from this equation. This here is a change of the force. How the force that is produced by this hydraulic cylinder, how that can be changed? Well, force, first of all, will be computed such the way that is pressure multiplied by corresponding cross-section area. So it's a pressure P2 applying this diameter of the cylinder piston. Okay. Now, if I want to change that force, I need to change the pressure here. Like I need to introduce a mathematical minor difference to pressure multiplied by corresponding cross-section area. This guy here. There's also pressure P1. Oh my, sorry, this is a P. It's applying here. So P1 is this guy here. P2 is this guy here. Same concept anyways. What about the change of the displacement? Change of the displacement will be because of the change of the volumes. Volume 1 and volume 2. So using this information, you can get how is a change of how much piston is going downwards. Okay. Now when substituting this information here, this information here is messy, I know it is messy. You could get the stiffness. Now we can use a definition of bulk modulus. And look at that. So the miracle happens. So using the bulk modulus, we can get the stiffness as it is mentioned here. Now this is the way you can solve this weekly assignment. So simply use, oh my God, it's a big mess here. Let me try to get some of the drawings off. No, that may be too much. Oh yeah, look at this. Stiffness, you can get it by substituting all the information to this equation. Okay, that's how it goes. Now, finally, with lengthy explanation, we finally able to do something fun. And something fun is this. Bulk modulus in hydraulics describes, look at this. So this is supposed to be squeeze number. I mean, of course, this is our first in-class squeeze today, but because I've lost the file, we didn't have the first in-class squeeze of the day. So bulk modulus in hydraulic describes what? Force produced by a cylinder, flexibility, compressibility of hydraulics, oil amount in hydraulic circuit, number of components in hydraulic circuit. Only one is correct. And now you can see that the game been on already quite a while. So let me see. Let me take my Socrative here. And let me see how many answers I have. Oh yeah, I have 75 students, 75 answers. Okay, I'm going to still make this a bit smaller. Like this. And success rate. Without further ado, I see that people are already in the game, so the cases are placed. My personal guess is 82. 82. My guess is 82. Okay, and the correct success rate value is, oh my god, it's here. It is here. Look at this. Look at what just happened. Look at what happened. It is 100%. It is 100% success rate. Huh. So look at this. Unbelievable. I don't know what to say. I really don't know what to say here. So, oh my god. How come? How come? You need to explain these to me because, I've been explaining all kind of things about multi-body dynamics, and many cases I'm telling you what is a correct in-class quiz answer, but always the success rate is less than 100%. Today, I did not even repeat it this so many times, and it's 100%. I guess that I don't know. Maybe I should have a break. This is too much. This is too much to handle. Okay, free beer. Yeah, if without the virus situation, for sure we would close the lecture, go and get the beer in this what is this called, street cafe that is located in a university. But bonus points to everyone. That is correct. So bonus points for all the participants. So that I will do for sure. So let me see if there is somebody that was actually guessing 100%. Do we have that kind of winners? But look at this. So you guys even didn't believe by yourself that this is going to happen today. No one. Oh no, there is. There's a guy that got 3 points from this because first of all, I'm sure it have to be correct answer. Then the lottery is correct, and then because the one extra points for all of you. But it's only one guy. No, it's two, 3, 4, 5. Good job. Oh yeah. I count four because if you look at in the very beginning, there are many guesses that says 100%. Okay, so very nice. Okay, I'm still not gonna close today's lecture. I'm gonna still explain you a few matters, but I kind of need some time to collect my thoughts because I got so confused. Oh my god! Should I take a screenshot of this? I think I need to take a screenshot. I need to send this to Rector directly. Hold on. Yep, now it is. Nice. So, okay. Yeah, extra points for all of you. And then here's another promise that I'm going to give it to you. I got to close early today. I'm going to close early today because I'm going to smile like a week from now. No, this is, this is so nice. Now, viscosity, that's what I'm going to explain to you next. I will be brief here, so I'm not going to explain that in details. Why? Because again, it's not that much needed in a mobile applications because it only takes place when the pressure difference is small. And we usually don't deal with cases like that. Now, let's take a look. How is that we can define the viscosity? Now we're going to look the definition of viscosity. And again, we're going to set up an experiment here. Now, a little bit of different kind of experiment than in the last time. This time, I'm going to have a base here. And the base is the one with the green color. So this is ground. And then I'm going to place plate a little off from the ground. Now what I will place between the plate and the ground is fluid. So this material here is not empty, but is fully occupied by fluid. Then what I will do then is that I will start introducing the force to this plate, and the amount of force is F here. And because of this force, this plate will travel with the velocity v. And now what happens when we are looking at the Newtonian fluid, and all the hydraulic fluids are considered as a Newtonian fluid? What happens in a particle level? This is again particle level. Remember, particle level. Particle level, this system behaves such the way that the particles that are standing or sitting close to the ground will have zero velocity. So they don't have any velocity whatsoever. Whereas the particles that are very close to this moving plate have exactly the same velocity than the plate. So they have a velocity v. Rest of the particles, the velocity is distributed linear manner. So the one in the middle will have half the velocity from the point of the plate. And this is how all the fluid that we dealing in the hydraulics are behaving. Okay, so now what I will do is that I will start looking these force a little bit. And one more parameter that I did not mention here is that the length or the width from the plate, from the ground, is assumed to be y. Okay, cross section of the plate is of course a here. Okay, so how much force is then needed? Well, the amount of force that is needed here can be computed as it is shown here. So it is a cross-section area of the plate. And then something that I'm going to explain you in a minute. So let's call it that as a mu. And then I have here this velocity. And the y that was telling you how far off is the plate from the ground. Now, this guy here is called absolute velocity. Absolute viscosity, not velocity, of course, but viscosity. And that describes the properties, the friction properties within the fluid. Friction properties, so how much friction is internal in the fluid. And that's something that we are after here. So we are after this component, but actually not this one, but it's a kind of constant what we are after. Now, using this relation that you have learned from the strength of the structures, which is a force divided by cross-section area, is a shear force. I can express the shear force as it is shown here. Now, as I mentioned earlier, all the fluids that are behaving according to this pattern are called Newtonian fluids. And this is only kind of fluids we are dealing with. Now what we're going to do is that we're going to convert this absolute viscosity to be something more practical. Something more practical comes into play when we are dividing this absolute viscosity by density. And now we're going to get this viscosity, which is called kinematic viscosity. Kinematic viscosity is something that we will then use when we are computing how much flow goes through the different kind of throttles when there is a small pressure difference. Now, this kinematic viscosity, when we are using the SI units, is having these units here. It's very often that you see, when you look at the viscosity, you see the units that are actually provided from the Society of Automobile Engineering. So this is what you go and purchase the oil to your car or motorcycle or whatever means vehicles you want to use. Usually you want to get the viscosity based on this Society of Automobile Engineering. This is related to these SI units, but it's not that straightforward relation. This table tells a little bit about how they are connected. Now, viscosity is a nasty feature of the fluid. And why it is nasty feature of the fluid? Because viscosity is a function of temperature, many others as well. But the temperature particular is the one that it is heavily a function of. Here's one experiment, one example. In this one example, I have here x-axis, which is a temperature. And then this is in a y-axis, I have kinematic viscosity. And to be able to express this, I even need to use I even need to use a logarithmic scale. And what the heck is going on here? Because look at this. Look at this. success rate is no longer 100%. What is this? So we got the one last minute student, and the last minute student voted incorrectly. We are not gonna, that makes no difference. We're still gonna be happy. We are still not gonna make any, changes in that regard. Okay, anyways, in this logarithmic scale, you see that, the temperature is really, really affecting seriously to kinematic viscosity. And that's why there's a recommendation, or actually was a recommendation, that whenever you wanted to get full power from your engine, you should make sure that the temperature of the engine is not too low. That means that you need to be in a certain particular point in this scale, because if you started here, then this kinematic viscosity is very high, and it may restrict the flow rate in the system, and it may not be able to produce enough pressure in certain locations. Okay, let's just shortly, I'm going to show you where exactly you need this kinematic viscosity. I can see that there's a little bit of discussion because of this last minute student. It's very unfortunate, I can tell you that. But it's okay. We're still going to celebrate. We're still going to celebrate, and we're going to close early today. So let me see. Where is my examples about? Hold on. I need to scroll down all the way. No, here. Now, this is not the example that I want. So where is it now? Maybe I lost that. Hold on. What is this? This is... Yeah, I'm not going to find it in this second. But anyways, there are a lot of these pre-computed tables that you can use to compute the flow rate to the different kind of drillings. Okay, but I'm unable to find that slide right now. Okay, line fluid theory. That's my last explanation for you today. And there are comments about this last minute student that voted incorrectly. Not voted, but entered their answer incorrectly. Well, it is what it is. But no, I still need your attention for next, let me think, 20 minutes or so, 15 minutes only. So we're going to look at the line fluid theory. This is, as I mentioned earlier, extremely important. It is extremely important because that's the one we're going to use to compute the pressures in different locations of hydraulic circuit. Why we need pressures? Because eventually the pressure applies in actuators. And let's say that we have a simple hydraulic actuator like this one here. And then we know the pressure here, P1, and we know the pressure here, P2. This is an information that we need in order to predict how much force is produced by a hydraulic cylinder. Of course, it goes similar way that I explained earlier. So the pressure of P1 will be multiplied by a corresponding cross-section area, which is this cross-section area. P2, which is applying in another direction, will be multiplied by this piston area minus piston rod area. So that's called as a P2. So we need these guys. This is what we need in order to predict the forces. How will you make it happen? Well, it will be with help of line fluid theory. And in a line fluid theory, first of all, we're going to divide the hydraulic circuits within the volumes where we are assuming pressure to be equally distributed. Okay, what that means, I need to get back to that in a second. I need to show you a few examples. But basically means that there is a container which there's no internal pressure losses. And this area of the piston is one good example. You can easily assume that the pressure this corner is exactly the same than pressure in a lower left corner. Yes, it is. It's same. So there's no pressure losses internally. And if that's the case, then we can compute the pressure in this particular location and in this particular location and other locations when there is no internal pressure losses. Okay, so that's how it happens. All right, so it's mentioned that non-fluid theory is very often used. It is very often used, and even those modeling softwares like Amesims, they still based on kind of the version of this non-fluid theory. Not kind of the version, but a version of the non-fluid theory, and it can be applied to well all hydraulic circuits. Basically, it's very general. It is not capable to apply acoustic pressure waves that sometimes takes a place when there's a really fast components. Like sometimes when there is this direction valve and when there's a very high end direction valve, it can be open and closed really rapidly. Sometimes it's open and closing can introduce waves, pressure waves that are traveling back and forth in this pipeline. This is something that we cannot take into account. But other than that, it's very accurate. It's very, very often used. Here it is mentioned. So mobile machines. So in mobile machinery, heavy machinery, it is very often that the pipelines are short. Work cycles are relatively slow. Relatively slow. In that case, the pressure losses are not usually very significant, so we can ignore it. Okay, so let's. This is too much to read. Let's look at the picture in a second, but just summarizing. So, non-fluid theory is all about this dividing hydraulic circuits into certain volumes. Once we have these volumes, then we can create the differential equations to describe the pressures within these volumes. Next slide will tell you the whole concept. So even don't bother to read this stuff because it's not that important. Other components, I mean, all other components like valves, direction valve, pressure valve, flow valves, each one of them will be modeled as a simple throttles. Simple throttles that may have flow area that is a function of time. But that roughly a nutshell of the modeling of hydraulics based on the non-fluid theory. Okay, but here is a damper. Well, very simple fluid damper. So how is that we can compute the force produced out from this damper? Okay, well, we need to know the pressure this side of the piston, and we need to know the pressure this side of the piston. We can consider this as a very simple hydraulic circuit. Okay, then comes the next question. Is it enough to know these pressures? So can we make an assumption that the pressure internally here, let's say in lower right corner is same that the pressure here in upper left corner? Yes, we can, because there's nothing that limits the flow to travel or particle to travel from here to here, back and forth. We cannot assume that the pressure here is same that the pressure here. Why not? Because the piston is made out of the way that there's only simple, very narrow trillings where the flow can travel back and forth. But because these trillings are so small, they will introduce the pressure differences. Now that's the idea of the whole damper here. Okay, so the pressure here and here are not the same. So that's why we have to use two volumes, volume 1 and volume 2, to compute force produced from this damper. Okay, so how it goes again, so this is a pressure 1, this is associated effective bulk modulus, remember the one that is affecting the flexibility, and corresponding volume size. Here I have pressure 2, effective bulk modulus, and the volume from this container, V2. Flow rate is traveling, now it's assumed that it's traveling from volume 1 to volume 2. No, it doesn't really matter what is a direction, a positive direction you put into this flow to have. It is just important that once you make a decision about the flow direction, you're just keeping consistent with your notations. How that will affect I will explain that to you in our examples that we are about to look a little bit later. Okay, so let's take a look. Here is more realistic hydraulic circuit. So we have here a pressure source, which in real life would be a pump, and pump operated by a motor of some kind. But let's just assume that there is a pressure source capable to produce constant pressure. It's going to be this one here. So this is my pressure source. And then I have my direction valve. Direction valve can have 3 different positions. Now I'm going to build these connections based on connections that is depicted in the figures. I need to make this off a little while so you can see how is connections in this case. So in this case, I'm connecting this port here and this port here. Maybe I need to make it a bit bigger so you can see that clearly. So these are my connections. If I would use this particular operation point, then that would introduce a different kind of volumes. All right. But now we're going to look this case here. And in this case, first of all, the pressure source is connected to direction valve. Then there is a hose or pipeline that is connecting direction valve to something that is called counterbalance valve. This is a figure of the counterbalance valve. Now, inside, here, or within this pipeline or hose line, we can assume that the pressure in the very beginning of the hose line is exactly the pressure when the hose line is about to end. Why? Because hose line is assumed to be somewhat small, and we assume that there is no internal throttles in this hose line. So that's why. Okay, this can be modeled by using this volume here. Again, we're going to compute the pressure here. There is effective bulk modulus and volume size. And then the counterbalance valve is connected to piston side. And then the piston rod side is connected here. This pilot drive is not modeled. It will be accounted when we are looking at how much is the size of this throttle, but it's not modeled directly. And again, here, this one is modeled here. This is a pressure here. This is a pressure here. So excuse me, that I need to remove. So this one is a pressure of the tank. So that's how it goes. And let me see. And then I have in-class quiz. And then the last thing that I will do for today is that I'm going to show you how these pressures can be computed. And then I'm done for today. Here's my in-class quiz, my next in-class quiz. For sure, this is not going to be 100% success rate. I'm asking, what is the volumes that you need to model this hydraulic circuit? And again, I have here pressure source. And then on the other side, I have a tank here. And I have a single actuated cylinder, so there is no connection from the piston rod side to anywhere. So the only fluid is applying here in the piston side. So what kind of volumes are needed to model the hydraulic circuit like this? And you take a look. So here are the options. This is the kind of like a two-way cylinder option. This is a one-way cylinder option. So that's the way that you are computing the pressure source, or in addition to pressure source, 2 pressures. And then there is a pressure source and then 1 pressure. Then there's a pressure source and 3 pressures. So kind of because this is, there is nothing in the piston rod side, it kind of means that this option is not very good option. So it leaves you 3 options, but out of the 3 options, what is the correct one? And game is on. So make your guesses. What is a success rate? Now, while you're doing your guesses, while you're entering your answer to this in-class quiz, I'm gonna take and explain how is that you can compute the pressures as a function of time. Okay, I can see that my streaming is heavily delayed, and let me see. Oh yeah, I started to collect some answers already. So let me get back to that. I will let you to think about this situation. And while you're doing that, I'm going to explain you how the pressures can be computed. Okay, again, how the pressures can be computed. Let me make an experiment here. I'm going to make a hose line or container. In this container, there is a mass flow that is coming in, a mass flow that is leaving from this control volume. Let's call this piece of hose or container as a control volume. Inside, within this control volume, there is a mass flow that is, well, it can be expressed that's the way that is density multiplied by flow rate. Okay, mass flow, again, mass flow in, mass flow out. So those are the kind of information that I need to know. Next, what happens is that we started to look how is that the mass within this control volume can change. Well, of course, it can change only if there's a difference between the incoming mass flow and leaving mass flow. And if this is bigger than this one, the mass started to increase. Another way around, mass started to decrease. Okay, so let's take a look at that. And I'm a bit worried that why is that we have no guesses about success rate. So are you guys not participating this last lottery of the day? Okay, I don't know. Anyways, mass of this control volume can be computed by using the equation that we know very well. So it's density multiplied by volume size. Okay, mass. This guy here can change, as I mentioned earlier, only if there is a difference between the incoming and outgoing mass rate. And again, if this is bigger than this, mass increases, another way around, it decreases. Okay, let's use this information here. Now let's see what happens. And when I'm using this information here, I can do this differential operations. That's the way that I have here. Density difference with respect to time, volume difference with respect to time. And still I have here mass rate in, mass rate out. Using this equation here, I can express this previous expression. So that's the way that there is a density with respect to time. This is a volume size density. Then there's a change in the volume with respect to time, flow rate in and flow rate out. And very soon we're here. Then I'm going to use this relation, which coming from chain rule of differentiation. Actually, this comes from the chain rule of differentiation. So volume change divided by volume is equal to the minus density change divided by density. And then when using the effective bulk modulus definition, I'm going to get this very critical relation which tells me how the density change is associated with the pressure change. Once substituting that to my previous equation, this is how it reads. And finally, the highlight is this. That now I'm going to get the first order differential equation, which can be written as P dots. This guy here can be said as a P dot is equal to the effective bulk modulus. Remember the one that is affecting the flexibility divided by volume size minus flow rate in. Flow rate in minus flow rate out. And then there is this term that is a function of volume change. That's it. This means here when there is a piston that is moving back and forth, that is the one that is changing the volume size. Otherwise, the volume is not really changing at all. This is it. So now what happens is that I'm going to go and take a look at the in-class squeeze. Now, let me make this a bit bigger. Okay, so there is quite a bit of students that I have not yet answered. And I know why, because maybe it's going to be hard to answer because if you don't know, these are the options. These are the options. So, hold on, that was a mistake. Okay, Now you know. Hope it is clear enough. I'm not going to show the option number, I mean the first option, because as I kind of already implied, is not a good choice, so don't select that. Okay, and where is my in-class quiz? Here. Okay, I have 80. Okay, 80 students. That's another great news, because 80 students means that I'm quite convinced that each one of you that are following the lectures will pass this course, because this is pretty much the only ingredient needed to be able to pass this course. You're following the lectures, you're doing okay. If you don't following the lectures, there's no way to survive, because how in otherwise you gonna learn this stuff about this land fluid theory and so on and so forth. It's gonna be very rocky road to learn that by yourself. But again, let me see. I'm still missing 18 students. So once I got the last students entering the answer, then I'm gonna close today's in-class quiz. I mean, this one. I do have one more left, but let's see if we have a time to do it. Okay. Okay, 11 students are missing, not more than that. I see that there is a serious delay, because what I'm explaining, think of this like 30 seconds delay, what I see that is streaming out. So that's why the communication related to this in-class quiz is a little bit cumbersome. Okay. Okay, 6 students are still missing, not much. And the game is on. Okay, my guess for this in-class quiz is that the success rate will be okay, last time I was guessing 75. This time it's going to be 65. 65. 65. Still, I like that somebody's guessing that there's 100%. Maybe it's going to be 100%. Let's hope that it's 100%, but we'll see. We'll see. 5 students are still missing. So very soon we're closing this in-class quiz. And once we're closing this in-class quiz, let me explain what happens after that. I'm going to show you what is the first in-class quiz in next Monday lecture. So you can already make a notes to yourself. And then we're going to close for the day. We're going to close for the day. Okay, so that's my plan. Let's see. 5 students. Maybe the 5 students are no longer with us. I guess so. So, so I got one more vote. Now you need to cast your vote, and then yeah, this is not going to be 100%, but we'll see how much it is. All right, so let me show the results to you. All right. Okay, but that's okay. Now we got the quite low numbers. There's 45%, 45%, which is okay, because remember we scored so well in the first in-class quiz that rest doesn't really matter. Okay, why this is correct? It's correct because it is assumed that this hose line here, it is connected to cylinder such the way that there is no pressure losses whatsoever, meaning that the pressure here is exactly the same that the pressure here. Sometimes there is because of these connections there may be a minor pressure losses, but typically you can make an assumption. This is a okay assumption to do it like this. Now this one is incorrect because there is nothing that comes from the piston rod side back to the tank. This could be okay as well, but that would mean that there is some kind of throttle that is introducing the pressure losses middle of the hose, and we don't have that. This one is incorrect because we don't need this many pressures to compute this. Okay, so what is the last in-class quiz, which I'm not going to ask today, but I will save for next Monday. I'm asking lump fluid theory ignores something. What is that? What is ignoring? Pressure waves, size of the hydraulic volume, physical size of the hydraulic change of size of hydraulic volume, physical size of hydraulic volume, compressibility of hydraulic volume. Compressibility, well, that it's there because equation is like this: flow rate in, flow rate out, and then there was this volume change. This is a compressibility, so it's there. Other components are there as well, but something is missing. So what is the missing? That is the thing that we're getting back on Monday. And I'm sorry, I promised to close early. I know that is about to get, to close this stuff, and that's what I'm gonna do. So see you in a second in team session. So thank you, and again, awesome stuff about the first in-class quiz. So here's when I'm gonna close today's streaming and recording. And see you next month.